So let's see those LP spaces. Oh, by the way, the L in LP, it stands for Lebesgue, of course. And we're going to use the integration to define the distances we need. Okay, so we need to define, so that's the idea. We need to be able to define an idea of distance in spaces of functions. So let's see the first one, what's going to be called L1. Okay, L1 of or. You can find some more detailed description notations, at least saying that it's or and with some specific measure, but let's not get into this. So it has a nice definition. It's very simple, actually, after what you already know. It's just the functions that are, well, measurable, but you know, that's just a keyword that appears everywhere now, and with finite integral of the absolute value. Okay, in other words, that's the space of integrable functions. Okay, and you remember that for a function to be integrable, it just means that f is integrable. It means exactly what we've written here, that the integral of its absolute value is bounded. Okay, strictly smaller than infinity. So we can define a norm. Okay, the L1 norm of a function f is just going to be defined, well, as simply as we can by this value. Okay, and as we said, it would be bounded, so that's fine, that it works. You can check that this satisfies the properties of a norm. That means it's definite positive. What does that mean? Do you remember? It means that it's always greater or equal to 0. That's for sure. So here of course, it's by positivity of the integral, it's going to be greater or equal to 0. And if ever we get equals to 0, that means that, well, we had the 0 function. Okay, that's definite positive. What are the other properties? We have the triangular inequality, meaning simply that if I do the norm of a function defined by the sum of two other functions, f plus g, norm 1, that's going to be the integral of f plus g, and of course you know, but this just comes from the triangular inequality on absolute value, that's going to be smaller than integral of f plus integral of g, so smaller or equal to norm 1 of f plus norm 1 of g. Okay, and finally we need for norm we need what's called homogeneity, meaning that if I multiply some function by some value, my function by some value k in R, and k is a real number, then this is equal to absolute value of k times the norm 1 of f, and again it's trivial to show it on this. And so it defines, using this norm, we can define a distance. And so we can say that, the distance between two functions in that space. So between two integrable functions, so the distance 1 in that case, it's just going to be given by the norm 1 of their difference. Okay, so that seems pretty nice. It can work also for complex functions. Instead of the absolute value, you use the modulus, but it's okay. So that's one thing. So now if I want to say that I'm considering a function that is integrable, I can just say, let's take f in L1, and that means it's integrable. Let's go for the next one, the L2 space. So again, if I've already stressed that it's going to be the most important space for us this year, and one of the most important spaces for applications. So what do we have? Guess what? We want f to be measurable, and instead of only the absolute value to be to get a bounded integral, we want that the square of the function is integrable. Okay, so that's also, you can also say it's the space of square integrable functions. Okay, all right, and of course, as maybe you foresaw that, we can define the norm 2 of a function that is in all L2 by saying it's going to be the integral of its square, but we take the square root. Okay, and okay, so maybe you see that. Next thing we can do is to define the LP spaces. Right, so it's just going to be the spaces of functions that are measurable such that the integral of their pth power is bounded, and so we can define the p norm of a function to be, well, the integral of f to the p, and we take the power 1 over p, exactly as we could define the LP norms in Rn. And we can even talk about L infinity, and that's going to be the space of functions that are called essentially bounded. What does it mean? Okay, it's going to be bounded. Well, to make it quick, you can just talk about the spaces of bounded functions. Bounded, but except on a set of null measure. Okay, so bounded almost everywhere. Okay, the thing is that maybe it's a bit more precise than that. For any value that you take, oh no, sorry about this. There exists a value m, and that's just going to be there exists m such that the set where the measure of the set where f is greater than this value is equal to 0, and then we can define sorry about this, m, the norm, the infinite norm of f to be this value m. In general, let's get rid of all the exceptional values of your function. If it happens on a set of null measure, just don't consider them, and you get that it's equal to the maximum or the supremum. More precisely, let's be more precise. Let's take the supremum of your function, the supremum of f on R. Okay, so that's just going to be bounded functions, and of course all these spaces are vector spaces. All these spaces are vector spaces. Sorry, vector spaces. Right, you remember just what it means. I can leave it to you to prove that. It's really, you remember, linear combinations of functions should be into this space, right? Maybe that's, let's talk more precisely about L2, because as I said, that's going to be our most important space this year. Well, let's prove that it's a vector space. What do we have? Let's take f1 and f2 that belong to L2. Let's take lambda that belongs to R. What's happening to f1 plus lambda f2? Okay, does that belong to L2? Right, so what should we show? We should show that the integral of f1 plus lambda f2 square dx is going to be bounded. Okay, so, well, it's just going, if you expand that, that's just, if you take the square of this function, that's just going to be f1 square plus lambda square f2 square plus 2 times lambda integral of f1, f2. Okay, so the thing is that from my hypothesis, I know that this is bounded because f1 belongs to L2. This is also bounded because, bounded smaller than infinity, because this one belongs to L2, but what about that? This is where one of our favorite inequality comes here, and I really want to remind you of the Cauchy-Schwarz inequality. Schwarz inequality. And more precisely, Cauchy-Schwarz-Bunyakovsky. That's also one of its names. Okay, what does it tell you? And that is something that is happening. Well, I haven't stated that yet, but this norm, the L2 norm, comes from the an inner product. Indeed, this one, you've shown this one several times last year, I'm pretty sure, if you write that the inner product between f and g is going to be the integral of f times g. Okay, remember that one? That's an inner product, so that now we have the inner product of f with itself. That should be the norm of f squared, and that's just going to be this one that we've already described. Okay, so Cauchy-Schwarz inequality works for all inner products. That's just going to be smaller or equal to norm of x2 plus, sorry, that should, I've lost my steps, right? Norm of x, if I take the square root, I don't need to, okay, norm 2 of x times norm 2 of y. Okay, so that means that in our case, that should be the integral of the product fg is going to be smaller than norm 2 of f times norm 2 of g. Okay, so that's a 2, right? So actually, it's a very usual proof that we did last year. I'm pretty sure we did that last year. So, okay,